Atomic structure and isotopes. Hopefully we remember most of this, but just in case, we're going to do a little recap. So protons, neutrons, and electrons are still the only three particles that we focus on in AP Chem. Protons and neutrons are, of course, in the nucleus, and they make up the majority of the mass of the substance. Electrons are out here in what we call the electron cloud. Couple things to point out. We measure the mass of protons and neutrons and electrons in a different unit than grams because they're so small that their gram value is teeny. So we kind of created this new unit called the atomic mass unit, or AMU. And we usually summarize that protons weigh 1 AMU, neutrons weigh 1, and electrons weigh 0. That's not technically accurate. We've done better research now and we've gotten more accurate results. So you can see here protons and neutrons actually do weigh slightly different. Neutrons weigh a little bit more than protons, and that'll kind of matter later when we're talking about atomic mass. And then electrons, of course, we round their mass to 0. But they are particles of matter, so they do technically have mass. They're just almost 2,000 times smaller than a proton or a neutron, so we just round it to 0 when we're talking about atomic mass. When you're reading the periodic table, you of course need to remember that the atomic number is the most important one, and that's going to be equal to the number of protons found in the nucleus of every atom of that element. So every single atom of carbon has to have 6 protons, or else it's not carbon. The atomic mass is a little bit more adjustable. It's usually the number of protons and neutrons added together, but you'll notice that the masses on the periodic table are not whole numbers. Okay, if we go back to this idea that they don't really weigh 1, that's one of the reasons. The other reason is that not all atoms of the same element have the same number of neutrons, but we'll get into that in a second. The hidden information in the periodic table is how many electrons there are. So usually we assume that we're looking at a neutral atom. And if we know that protons are positive and there are 6 of them, if we're assuming that this is a neutral atom of carbon, then that means there would also have to be 6 negatively charged electrons for the 6 positives to be canceled out. So the atomic number represents protons and electrons. The atomic mass represents the neutrons and the protons added together. So why is the atomic mass not a whole number? Okay, it's because not every atom of the same element has the same number of neutrons. So for example, carbon, there's one version of carbon, which is very common, 98.9% of it, where it has 6 protons and 6 neutrons. But there's also about 1% of carbon that has an extra neutron. And then there's a really small percentage of carbon that actually has 2 extra neutrons. And that's going to affect what we would consider the average mass, because if some atoms of carbon weigh more than 12, you can't really say that carbon weighs 12. You have to account for the fact that a few atoms in a handful are going to weigh a little bit more than 12. The periodic table can give you kind of a clue about which of those isotopes is the most common version of that element and which one would be less common. So for example, if we're looking at boron, we can tell by its atomic mass that probably, if we're thinking whole numbers, because there can only be an exact number of protons and neutrons, that it usually weighs 11. And if you look at this chart, you see that boron 11 is about 80%, whereas boron 10 is about 20%, which is why we see that 20% loss right there, and it's 10.8 instead of a rounded 11. So if you're looking at an isotope notation, not only can you tell how many protons, neutrons, and electrons it has, you can also now determine, is that a common version of that element or is that an uncommon one? So if I was going back to this, I would say boron 11 I would consider the common version of boron, whereas boron 10 is the uncommon version. So if I'm breaking this down, I can tell based on the atomic number, which is always written at the bottom, that potassium has 19 protons. If I do 39 minus 19, then that means it has 20 neutrons in the nucleus, and the lack of a charge means I'm going to assume that I'm balancing my 19 protons with 19 electrons. This other way of writing an isotope notation just takes the atomic number out and writes the mass next to it. So saying 19 next to potassium is not actually necessary, because if it's potassium, it's always going to be number 19. So I know that it still has 19 protons. It's still not charged, so it's going to have 19 electrons. But this isotope of potassium has 40 as its mass instead of 39, so that means it has 21 neutrons. If you're following this up with the idea of commonality, which one has the highest relative abundance, on the periodic table, potassium has a mass of 39.1, so that means that this would be the more common version. When an isotope is charged, you'll see the charge written in the top right corner like this, and you'll have to adjust charge based on the idea that only electrons can be gained and lost from that electron cloud. So this has 20 protons, 41 minus 20 is 21 neutrons, and the idea of the positive charge means that you now have 2 more positives than you have negatives, so that means that this atom has lost electrons and now only has 18 instead of 20. And the other thing that we can ask ourselves now is, based on the idea of relative abundance, is this a highly abundant version of calcium or is it a low abundant version? So since calcium weighs basically exactly 40, I think it's 40.08 on the periodic table, that means 41 would make this a low relative abundance. It would be uncommon. Last but not least, we'll look at this negative one. So we have 7 protons, 14 minus 7 is 7. Negative 3 means that we've gained 3 extra negatives compared to what we had before. So that means we have 10 electrons. And then if we are considering, is this a common or uncommon version of nitrogen, on the periodic table, the mass is 14.01. So that means that this would be a very common version of nitrogen. So if we put this idea of the average atomic mass representing the commonality and uncommonality of isotopes, we're going to look at an equation like this. So the atomic mass of an element is determined by the sum of the mass of the individual isotopes times their relative abundance, and then you would add all of them together. So if we do a simple one, like there's only 2 versions of copper, copper 63, is 69.09% abundant, and it has a specific mass of 62.93. So remember, protons and neutrons do not really weigh 1, so we want to account for the fact that we have a more specific mass than just 63. And we know that copper 65 has a mass of 69.93. So the missing piece of information that we're going to need, we need to know the mass and the percent of both of these isotopes. The question doesn't directly give you the percent of copper 65, but it does give you what you need in order to figure that out. Obviously, if there's only 2 isotopes, then their abundances would have to add up to be 100. The key to getting these questions right is to remember that you need to change the percentages to their relative abundance numbers, which is going to be the percent as a decimal form. So I'm going to take my 69.09% of the copper 63 and 30.91% of the copper 65. If you multiply and add those together, you'll get the atomic mass of copper. Since the questions gave me 2 decimals as a measurement and the atomic mass unit as the unit, I'm going to keep 2 decimals there and have the correct unit. It's not in grams, it's in AMU. The nice thing about this is you can always check to make sure your answer is right, because it should match the periodic table. So let's say you're looking at an isotope with more than, or not an isotope, an element with more than 1 or 2 isotopes. So like this one has 4. You can also just use these results of what's called a mass spectrum, where all of the different weights of isotopes have been separated and calculated in comparison to each other. This graph doesn't give you a ton of information in terms of mass, but you can still do your math using that equation from the previous question and figure out relatively what the answer is, because the ultimate goal is to identify the element, not have a super specific mass. So if I set this up, I had to kind of estimate my percentages, but I did make sure that they at least added up to be 100. I'm going to get 87.69 AMUs, which is pretty close to strontium. So I'm going to go ahead and assume that that is the correct element.